Yes, hello everyone. So today we are discussing a question based on EMI, electromagnetic induction. It's a very interesting question because it's a mixture of electromagnetic induction and oscillation and waves concept. Okay, so let's understand this. The question says a conducting wire of length L and cross section area A is taut between two fixed grounded metallic supports and is vibrating in its fundamental mode with a frequency V and amplitude A in the presence of a uniform magnetic field of induction B pointing normal to the plane of vibration of the string. Okay, so as per the question, they are showing the magnetic field to be outwards. Okay, find an expression for electromotive force induced in the wire as a function of time, assuming the wire's straight at time t equal to 0. So, as per the question, they have given one diagram. I would like to draw that diagram in a simple fashion for us to solve the question. So, let's say this is one support, and we have other support somewhere here, and the string, let us say, at this moment is like this. Okay, at some random moment, the string is in this way, and this is the other support that we are having. Okay, like this, we are having the support. Now, the length of the string, which was taught, right? So they are giving that length to be as L, and amplitude of oscillation, the maximum, the node location, the amplitude, they have given it as A. And what else? Frequency. They have given the frequency of the oscillation to be V. I mean nu, we should call it as nu. That's it. These are magnetic field induction is B. So they have given the magnetic field also acting in this region like this. So like this, magnetic field is acting throughout the region. All right. Now, if you think about this, just think about it. What's happening really is the wire which is stretched there, it is undergoing an oscillation. Every point or every particle of this wire is undergoing an oscillation with different amplitude. The amplitude varies as I move to the right side. At the node location, that is anti-node location, I am experiencing the maximum amplitude. At the both extremes, I am having node, so amplitude is zero. So amplitude keeps changing. But we have studied this in the waves chapter, standing waves concept, that all of this entire string would be coming to this location of zero displacement at the same time, right? The entire wire would be coming to this dotted line region at the same time. The entire wire, all particles would be reaching to its maximum amplitude also at the same time. So you know how this oscillation or this wave, standing wave, actually happens. Now, based on this, we want to find out the EMF. That's our question, right? So can we use the concept of BLV, that is emotional EMF, right? Every particle or every small section of this wire, let me do like this. Let me go to a location X from here. At this location, if I think of a small section whose thickness is dx, then this small dx is actually performing an SHM in this way, right? It will be going up and down with a displacement of y at any given time. This displacement equation can be obtained as y is equal to, if you remember the standing wave, we have an equation a sine omega t and cos omega t, and like that there will be a kx sine kx or cos kx term, if you remember this, right? So same equation I'll have to use, but while using the equation we need some condition, like what the string is actually doing at time t equal to 0 and x equal to 0. So according to the diagram, when x is equal to 0, what at x equal to 0, I'm always having a node. That means when I put x equal to 0, my answer should become 0. Why? The displacement should become 0. So when x equal to 0, displacement has to be 0. That only happens for a sine function. And same way as per the question, at time t equal to 0, they're giving in the question, at time t equal to 0 also, the wire is on horizontal like this, right? So that means at time t equal to 0 also, displacement is 0. This can be satisfied only by using the equation y equal to a sine kx and sine omega t. Both of them should be a sine function. Then I put t equal to 0, I'll get the answer y is equal to 0. Or if I put x equal to 0, then also my y is equal to 0. These are kind of like boundary conditions, we say. Using those boundary conditions, we have fixed the equation how it should be. Now, if I want to find out the EMF induced, I can very easily find out for this small section I can say the DE, the small EMF induced, is equal to the magnetic field B into L, the small length, that is dx I have taken, L into V, whatever velocity it is having. Now this velocity is not given in the question, but we can very easily find this velocity by using the oscillation or the wave equation that I'm having. So if I differentiate this, basically dy by dt, okay, that is the velocity of the particle, right? So we can get velocity v is equals to differentiation of this with respect to time. This is a constant. We are talking about a particular location. At a particular location, my x is a constant, right? I'm calculating this, or I'm deriving this equation of velocity with respect to time. So at any given position, that's not a variable with time. X is not variable with time. So therefore I can say a into sine kx, being a constant written as it is, differentiate the variable, that is this one. So it will become omega times of cos omega t. You'll be getting this. Just take the omega this side. You'll be getting it as a omega sine kx into cos omega t. This is your equation. Now that is your velocity. We can substitute that here. So b into dx into velocity would be a omega sine of kx cos of omega t, right? Okay, so let me write all the terms which are constants together. So b a omega sine of kx and cos of omega t dx. This is the EMF produced by a small element which is performing oscillation like this. Like that, I am having many elements on this wire. And if you think of them, all the elements are actually connected in a series manner, right? You will be finally finding what, the entire wire would be made up of many batteries, for example, like this. Now, which side positive, which side negative, that can be also said. While going up, velocity is in upward direction, so one side positive, one side negative. While coming down, the velocity direction changed, so the battery orientation will also change. So I'm not finding which how the battery orientation is, because for half of the journey I'm having one, other half of the journey I'm having other orientation. We should know that the EMF induced at each and every section, each and every small element of this, they will be all in series, because then only they'll become a full wire, right? They're all connected in series, one end to other end, like that. So I can find out the total EMF. That's the whole point. Total EMF is equal to integration of dE. Because they're connected in series, the EMF should be basically added. So integrate it. What's the variables here? I'm integrating with respect to x, because right now I found out EMF at a particular location. I want to find everywhere. So integration is happening with respect to x. So this x term is a variable, remaining everything is a constant. So take everything outside. So I'll be getting b a omega cos omega t outside, integration of sine kx dx. Okay. Now what is the limit here? My limit is going from x is going from 0 to L. This would be my limit. Okay, now I can apply the integration, and I'll be getting it as E equals to b a omega cos of omega t, and this would become sine integration will become minus of cos of kx by k, limit going from 0 to L. Yeah, minus you can take outside. So you'll be having minus b a omega by k cos of omega t, and this, if you put the limit, you'll be getting cos of k L minus cos of 0. Okay, now what is omega by k? If you remember, omega by k is the velocity of the wave, omega by k. So I can write it as minus of ba velocity or speed of wave. I'm specifying that. Don't consider it as speed of the particle. Speed of particle is different. This was the speed of the particle, Vp, we are talking about. This was the Vp, speed of the particle. This omega by k is the speed of the wave. And this is cos omega t as it is. Now, what about this? Cos of k. What's actually the formula? It's called as wave number, right? If you remember. So you can write it as 2 pi by lambda. That's the formula. Into L. Now they have specifically said that this is actually fundamental mode. If you remember waves chapter, for fundamental mode, we say that lambda by 2 equal to L. This relationship is there. So wherever I am finding the L, instead of L, I can put it as a lambda by 2. So if I put lambda by 2 minus cos of 0 is 1, I'll find that this lambda lambda cancel, 2 cancel, I'll be having cos of pi, which is minus 1. So minus 1 would be minus 2. The 2 can come this side and minus will go. So basically 2 times of b a velocity of wave. How do we write a velocity of wave? Shall we write it as you remember this ninth grade concept, speed of the wave is equal to lambda by t, and 1 by t can be also called as lambda into frequency, right? In our question, the frequency, they're calling it as nu, so I'll write that. So velocity of wave is given as lambda into nu into cos of omega t. This is what I'll be getting finally. Now again, lambda is not given in the question. What is given in the question is the length. So shall I write this in terms of length? So what can I write? I can write it as 2 times BA. Instead of lambda, I can write it as 2L times nu cos of omega t. That's it, over. So I'll just write down finally the answer here. The last thing that we're getting is E is equals to 4BAL nu into cos of omega t. So what I have got here is the equation of EMF. I got the EMF as a function of time. At different moment of time, I'll be having different EMFs. The EMF sign will be also changing. See, it is coming as a cos. So for half of the time, it will be positive, and the remaining half time, it will be negative. So that's what I said. When the rope is going upwards, it is having a velocity in upward direction. When the rope is coming down, it's having velocity in downward direction. That means the EMF would be also switching. We know the concept of motional EMF. It depends on the velocity, which side positive, which side negative. So accordingly, we have got the answer. A very interesting and a nice question. This kind of questions is what the JE prefer. They are mixing up the concepts from the 11th grade of oscillation and waves with the 12th grade electromagnetic induction. So I'm hoping that you have understood this. So let's stop here. Thank you.